Good evening. Welcome back to the course on electronic packaging and manufacturing. And today we start on a very important topic, which is on thermal design and cooling. Okay. Let me start by saying that if you look at electronic products and even packages or systems, and you look at the causes of failure, majority of that can be attributed to overheating due to thermal, if I may use the word, mismanagement. So, why does this happen? Okay. So, let me take a step back and try to explain why thermal management is important. When you have a circuit or when you have a circuit board or a device, let us take just the microprocessor for example. When you switch it on and you have all this circuitry working inside, we know that there will be heat generation because of losses, I squared R losses, joule heating. So, this heat, if not removed or dissipated efficiently, is going to lead to a rise in temperature. Okay. And finally, every device, because of its material constraints as well as as well as the requirement for proper functioning, has a certain threshold temperature beyond which it cannot operate. Either its performance goes down and in the worst case it just gets damaged, or if I may use loosely a term called fried. Okay. So, as the heat is getting generated, it is important to remove the heat efficiently, so that the temperature remains within that acceptable threshold. Okay. Now, what is the problem here? If you look at this VLSI, very large scale integration, ULSI, ultra large scale integration, and also if you look at the system level. So, one VLSI is within the microprocessor or the chip, where we are packing in more and more circuitry, right. Today, in a, let us say a silicon chip of 1 centimeter by 1 centimeter or sometimes even less, you have millions of transistors inside. Okay. Each of them probably dissipating a few milliwatts, but you add them up, you see how much of power it is dissipating. Okay. Similarly, if you look at a system, if you look at your laptop computer for example, we have so much of features inside. We have a microprocessor, which is a CPU, we have the graphics, we have memory, we have wireless, we have this controller hub, we have the optical disk drive, the ones that still come with the optical disk drive, the CD drives, you have the hard drive or the flash memory or the flash drive, and then you have all these other components like the voltage regulators, VR, and the passives, amplifiers, power converters. So, all these are all accommodated in that small 13-inch box. If you look at my laptop computer here, this is one of these mini ones, okay, 13-inch, a motherboard inside consisting of so many different processors, each of which is dissipating heat. So, how do I remove this heat? If I do not remove, it will keep getting, the temperature will keep rising and it will come to a point where it will fail. Okay. So, thermal management is about that. Okay. So, one thing is, it really, the way I described it, it really comes as an afterthought, and it is like the electrical designer or the architect, as we call it, the VLSI architect. He designs the microprocessor and that dissipates, let us say, some x watts when it is powered on, and then the thermal designer needs to design a cooling system which can dissipate this x number of watts while keeping the temperature within the acceptable limits. Okay. And unfortunately, this is how for many years the design used to happen. it was called the over the wall design. Okay. The electrical and thermal engineers would work in isolation. The electrical engineer is going to design, come up with his design, and then it is over the wall means he will just throw this design over the wall, and the other end of the wall is where the thermal engineer is present, and he takes it and tries to solve his problem. Okay. But things are changing now. Okay. Now, the amount of power that you can dissipate, and therefore, the amount of circuitry that you can pack into your microprocessor is a lot of times limited by the thermal design, limited by temperature. Because with products becoming smaller, thinner, etc., the kind of thermal solution, the kind of cooling that we can offer using traditional methods is really going down. So, therefore, the thermal engineer will step up and say that, look, I am sorry, I cannot cool beyond this. Okay. And therefore, I want to introduce this term today called TDP. A microprocessor has something called a TDP, standing for thermal design power. Okay. So, the maximum power that can be dissipated during operation by a microchip is limited by its TDP, standing for thermal design power. Okay. So, you can understand the importance of thermals in electronics. Okay. Thermal management is extremely critical. The unfortunate part is it's not something that comes to the forefront. Number one, you are not going to buy a system, an electronic product, because it has a very cool thermal solution inside. Okay. If a product works according to its specification, then that is what the user expects. If the product does not work and gets overheated, that is when the thermal engineer gets blamed. Okay. So, many a times people say that a thermal engineer's job or thermal is in this industry is kind of a thankless one. It is very important, but it is a thankless job. So, one of my friends who used to work for HP, he used to say that our work is like that of a janitor. You know, people will come and make everything dirty, and our job is to clean it up. Okay. One of my favorite analogies is, if you think of a building, okay, if you think of a building and it is a very nice one, and you go and you like it, you give compliment to the architect and to the builder, right. But what we forget is the building is running efficiently, and there are lots of other things that is involved there. There are the plumbing lines, there are the electrical lines, there are the fire safety and water lines, and all these. I mean, if they are there, yeah, they are expected to be there. If they are not working, of course, all hell breaks loose. Okay. So, the role of a thermal designer is similar to that electrical designer in the building, or the the hydraulics engineer. So, or the one who designs his water system and so on. Okay. So, what I am trying to say, it is extremely important. You cannot imagine a building without electricity. You cannot imagine a building, staying in a nice building, but where there is no water, right. You expect that, but if it is there, yes, I mean you do not say, oh, what a wonderful job this designer has done. We do not say that, right. So, similarly, so that's there, it's important, we have to do it, and we have to understand that a thermal designer, even though it's very critical and important, you ask anybody, they will anybody who works in that industry, they will say, oh yeah, it's very, very important. Some people will say, oh, you thermal engineers are very painful, you don't let us add more features to the circuitry, we know how to do it. I have space, I know of an architecture where I can have more and more features, I can have more speed, but you are not allowing us to do that. So, that is the way it is. All right. What I am trying to say is the importance of thermal designer in this industry. Okay. That is what I have been doing for the last 20 years or so. So, you can see, so if I get a little biased, and if I talk a little more passionately than the other topics, then I hope you will excuse me for that. Okay. So, thermal design, let us get into the topics now. The first thing that we need to understand is heat transfer. Okay. I think for people with mechanical engineering backgrounds, this may come as a repetition or as a recap, but for people from other backgrounds, I will try to make it, I will try to brush up the essential concepts, so that when we come to electronics cooling, you understand what we are trying to do. Okay. So, first we will talk about what is heat transfer. Okay. So, what is heat transfer? Heat transfer is energy in transit due to temperature difference. It is also thermal energy, we call it. So, heat flows or thermal energy flows from a higher temperature to a lower temperature. Okay. And for heat to flow, a thermal gradient, which is a difference in temperature, a temperature gradient must exist. So, if you have two bodies and bring them in contact, two bodies at different temperatures, one at a higher and one at a lower, and you bring them in contact, then we know that heat will flow from the hotter body to the colder body, right. And how long will that flow? The heat will flow till the two temperatures get equalized. Clear? So, that is what we mean when we say that a temperature gradient has to exist when for heat to flow. I am sure you have all studied thermodynamics, basic thermodynamics, and you recall second law, and this essentially tells the same thing. Okay. For heat to flow spontaneously, the direction is from higher temperature to a lower temperature. Second law, one of the statements suggests that for the heat to flow in the opposite direction, that is from heat to flow from a lower temperature to a higher temperature, that cannot happen unless you do external work on the cycle, right, or on the system, work done on the system, not by the system, right. So, we will talk about that, because when we talk about cooling techniques, we are going to talk about refrigeration, and refrigeration is an example where we use it every day in our refrigerators, in our air conditioners, where we know that the direction of heat flow is actually from the lower temperature to the higher temperature, and that is possible because we have a compressor which does work on the system. You spend energy to make it happen, otherwise spontaneously it will not going to happen. Okay. So, that was a little bit of digression, but talking about temperature gradient. Okay. Now, what are the three modes of heat transfer? We know from our class 12 physics, it is conduction, convection and radiation. Okay. So, conduction, convection and radiation. So, these are the three small cartoons that I am showing at the bottom of the slide, which tries to give you the essence of what each of these heat transfer modes mean or imply. So, let us spend a little bit of time on this slide, okay, because this is kind of, I am trying to brush up an entire undergraduate, at least one half of an undergraduate heat transfer course in one slide. So, let us try to do this. On the left hand side, what you see is conduction. Why does conduction happen? Conduction happen because of movement of molecules or lattice, vibration of molecules or lattices. Okay. So, the molecules at higher temperature vibrate with higher amplitude and pass on the energy to the neighboring molecules which are at a slightly lower temperature. Okay. And this is how the energy gets passed from the hotter temperature to a colder temperature. Okay. So, if you have a slab over here, as I am showing, you can think of it as a wall. If you look at a cross section of a wall, okay, and there exists a temperature gradient across the wall. So, you have a higher temperature on this left hand side and a lower temperature on the right hand side. If you do that, there is a temperature gradient that exists across this solid wall, as a result of which heat is going to flow. Okay. So, there is going to be conduction through this solid. Now, how much heat is going to flow? That is the next question. Per unit time, what is going to be the heat flow? Okay. So, the first thing is, so that is given by this expression K A delta T over L. Okay. So, I will take a step back and say, let us go back to the drawing board. This surface area is A, this thickness is L, this face is at T H, this face is at T C. Then Q is going to be proportional to number 1 T H minus T C or delta T. It is going to be proportional to the surface area A, and it is going to be proportional to 1 over L. So, therefore, the final expression that we write is A delta T is T H minus T C over L, and the proportionality constant is written as K, and K is known as the thermal conductivity. Okay. So, if we go back to this slide, that is what you see here, K A delta T over L. Okay. So, now this thermal conductivity is a parameter of importance. If the thermal conductivity is high, then it is a good conductor, thermal conductor. Okay. So, copper is a good thermal conductor, aluminum is a good thermal conductor, but let us say brick is not a good thermal conductor, rubber no, thermocol very low, it is an insulator, right. So, that is what it is. Now, let me also say that conduction also happens in a liquid or a gas, and the same expression holds good there as well. However, there may be other modes that may become predominant, all right. So, this is conduction heat transfer. Now, what is convection heat transfer, which is what is shown on the second picture over here, second cartoon. Convection is when, apart from just molecular vibrations, we also have what is called a bulk flow of a fluid. A solid cannot flow, a fluid, it can be a liquid, it can be a gas. So, therefore, the heat transfer is not just happening because of vibrations of molecules and transfer of internal energy from one layer of molecule to the next, but along with that there is some bulk movement of the fluid molecules, so that the heat is taken away. Okay. So, one example over here is, let us say you have a plate or a surface at a high temperature as shown here. Okay. And then we have it is placed in an ambient of at a lower temperature, and we have a stream of air blowing above it. Okay. So, the air is at a temperature T infinity, which is lower than T high. So, therefore, there is going to be heat transfer from this higher temperature to the lower temperature, high temperature plate to the low temperature gas, air, or if it can be liquid as well. So, the fluid that is flowing over it. Okay. If that is the case, how do I quantify the amount of heat that is dissipated? So, again, the amount of heat dissipated is going to be directly proportional to the temperature difference. It is also going to be directly proportional to the surface area of the plate. Okay. So, if this is my plate, then and it is held like this, then this is the surface area of the plate. Okay. And it is going to depend on this parameter small h, which is known as the heat transfer coefficient. And this heat transfer coefficient, unlike thermal conductivity, which is a material property, this heat transfer coefficient H depends on a variety of parameters. It is going to depend on the properties of the fluid, whether it is air, whether it is water, and those properties include, we will see later that properties include thermal conductivity, viscosity, density, specific heat, okay? And it is also going to be a function of the geometry, whether it is a flat plate or whether it is a cylinder or whether it is a sphere, whether it is a flat plate of infinite dimensions or whether it is a flat plate of finite dimensions. So, all those things. So, it depends on geometry, it depends on the fluid properties, okay. And it also depends on boundary conditions in terms of what is the temperature, whether it is uniform temperature, whether it is non-uniform temperature, so on and so forth. We will look at all those later, okay. But what I am trying to say is, unlike a solid where I say copper, okay, the thermal conductivity is 400 watts per meter Kelvin at a certain temperature. But for heat transfer coefficient, if you ask me, oh, I am having airflow over a flat plate, what is going to be my heat transfer coefficient? I will tell him, I will ask you, okay, airflow, okay, I know at least you have told me the fluid medium, but what is the temperature? Okay. If you tell me the temperature, I will ask, okay, what is the viscosity and specific heat and density and thermal conductivity of air at that temperature? Okay, you tell me that. Then I will say, all right, what is the velocity at which the air is coming? Okay. Then what is the temperature of the air, difference between the plate and the air? Finally, what is the condition of the flat plate? Are you maintaining at a uniform temperature or is the boundary condition something else? And what are the dimensions of the flat plate? Okay. So many questions on which heat transfer coefficient is going to depend on. Okay. So, it is not that easy. In fact, people who do research on heat transfer, convective heat transfer, a lot of research goes into determination of this parameter H or heat transfer coefficient or some form of heat transfer coefficient, all right. Then what we are going to, then the third mode of heat transfer is called radiation. Now, what is radiation? If first of all, what is radiation? Okay, it is an electromagnetic waves that is generated by any surface which is at a temperature above absolute 0. Okay. If a surface by virtue of being at a temperature above absolute 0 emits radiations. Okay. Now, the amount of radiation that it emits depends on several factors, but also is proportional to the fourth power of its absolute temperature. Okay. Now, similarly, if you have another surface which is at a different temperature, that also emits radiations, okay. And that emitted radiation is going to depend or is going to be proportional to the fourth power of the absolute temperature of this second surface. Okay. Now, what is the net exchange between the two? If you have two such surfaces, then what happens is the radiation emitted by surface 1, part of it falls on surface 2. Similarly, the radiation emitted by surface 2, part of that falls on surface 1, and the net exchange therefore is the difference of the two. Okay. In a very simple case where the it is one surface that is emitting radiation and which is received by a large surface around it, in that case a simple expression as shown over here, sigma epsilon A, which is the surface area of that plate that is emitting radiation and that is at the higher temperature, times the difference of the fourth power of their absolute temperatures. Okay. But mind you, this is a very specific case. So, we need to keep that in mind. All right. So, actually there is also something called a shape factor or view factor that comes into this expression, and which is important because shape factor determines that how much of the radiation emitted by surface 1 actually reaches surface 2. Okay. So, that is one. The other thing that I want to tell you is the fact that let us also talk about what each of these terms mean. Epsilon is known as emissivity. Okay. So, the amount of heat that is emitted, apart from depending on the fourth power of its absolute temperature, also depends on the emissivity of the surface. Okay. And emissivity typically lies between 0 and 1. When the emissivity is 1, it is known as a black surface, okay, sometimes also called a black body, but radiation, when we talk about radiation heat transfer, it is more about surface. So, we will call it black surface, and something that is whose emissivity is lower than 1 is a non-black surface. Okay. Emissivity can be a function of wavelength, and sometimes what we do is we take an average value of the emissivity over the wavelength, the thermal wavelength or the range of thermal wavelength, and we give it a constant value, and at that time, and that is called a gray body approximation. Okay. So, the emissivity of a surface typically is a function of the wavelength, but if it sometimes what we do is we plot emissivity as a function of wavelength and give it an average value and call it the gray body approximation, and we say okay, this surface is a gray body with emissivity of 0.7. Okay. So, 0.7 is actually a mean value, and it helps us in calculations, that is it. Okay. So, I think I am giving a little more details than required, but what I am trying to do here is give you a recap of the basic modes of heat transfer, okay, because this is very important. I will just end this slide and probably this lecture as well with a last point, which is on convection. So, convection again, as I said, is of course when there is a bulk movement of the fluid, and the bulk movement of the fluid can happen either by spending external energy. For example, I am showing here that air is flowing, and why, how can this air flow? The air can flow because if I put a fan, let us say, at this point and blow air, or a compressor and blowing compressed air, or a pump and blowing and pumping a liquid, right, and I am doing external work on that, and I have to spend energy to do that, and that is called forced convection, because I am somehow forcing the fluid to flow over this heated surface. So, it is called forced convection. But sometimes if I do not do anything, right, if I just take our experience says that, right, if I just take a heated solid surface and place it on my table, it is going to get cooled. How? It is going to get cooled because of natural convection. I am not blowing air on that, but it gets cooled. Why? Because the air that is right next to the hot surface will pick up heat, and as it gets heated, its density goes down, it becomes lighter, it moves up. As it moves up, there is a partial vacuum created, and cold air from the surrounding comes over here, comes down to occupy that void, which in turn again gets heated and rises up. So, this is natural convection occurring due to density difference, right. So, it is also, the technical term is buoyancy induced flow, because of the buoyancy forces resulting from difference in density. All right. Of course, natural convection is a less efficient means, but it comes for free, you do not do anything. Forced convection, definitely the rate of heat transfer will be much faster, but then you are having to use external energy either to power the fan or power the pump or the compressor, whatever it is, whatever is your prime mover. Okay. So, I will just end this lecture on this topic of forced and natural convection by this analogy. Okay. You have a very hot cup of tea and they give it to you, and it is so hot that you cannot drink. What will we do? We are going to either leave it on the table so that it gets cooled with time, and that is going to be natural convection. But if I am in a hurry, let us say I have to go to a class or I have to go to a meeting and I want to have the tea so that I am alert or whatever. So, in such case what I will do? I will try to take it and blow air on top. What am I doing? The second one is forced convection, not by a fan, not by a pump, but I am using the energy from my lungs to blow this air above the hot liquid, so that the amount of heat transfer, the rate of heat transfer is increased. It would get cooled faster, and so I can drink it and go to my meeting. Okay? All right. Thank you very much. And when we come back next class, we are going to take off from here and talk about the concept of heat flux and thermal resistance. Thank you very much.